In today's lesson, we are going to look at reasons for factoring. So we spent this whole unit on learning how to factor different expressions, different quadratics, different types, getting, getting them into their factors. Now we're going to look at the reasons for doing that. So just a little bit of review, going back to the last unit, we want to write the equation in all forms of the quadratic for this graph. So we're going to start off with the vertex form. That is one that should be a little bit more familiar. That's the one we dealt with quite a bit in the last unit. Y equals a x minus h squared plus k. Again, our h and k come from the vertex. So in this case, it is 2, -1. So that means in our equation, we're going to have y equals x minus 2, opposite of what we see for that x value, squared, and then we're going to have a minus 1. The a value, remember, it comes from our step pattern. So in this case, we go over 1, up 1. So the first step is 1 over 1, up 3. That's our next step. If we're trying to determine the a value, all we really need to worry about is that first step. So whatever that first step is, that a value, that is going to tell us, that first step is going to tell us our a value. So in this case, our a value is going to be 1. So I could just write my equation as y equals x minus 2 squared minus 1. I don't really need to show that a value of 1. X minus 2 squared minus 1. Now for our factored form, and actually let me just change the different forms to a different color. So for my factored form, if we remember from the last unit, our factored form is y equals a x minus r times x minus s, with r and s being our x-intercepts. So in this case, if I go through and I look, I can see it crosses the x-axis here at 1, 0, and it crosses here at 3, 0. So those two values are going to be our r and s. So we have y equals x minus 1, again, opposite of what we see, so minus 1, and x minus 3, opposite of what we see again. We still need an a value. In this case, we don't have to worry about finding it again because it's going to be the same as the other form. Right? The a value stays the same in all of these forms. So y equals x minus 1 times x minus 3. Now for our standard form, we haven't quite dealt with a lot, but our standard form will be in the form y equals ax squared plus bx plus c. Now we haven't dealt with this form before, but if I look at this standard form, it does look like a trinomial. And we've dealt with trinomials before. So if I look at my factored form as a pair of binomials, or like a product of, or two binomials multiplying each other, if I expand them, similar to what we've done at the beginning of this unit, if I expand my factored form, let's see what we get. So we have y equals x minus 1 times x minus 3. Expanding means to use the FOIL method or distributive property. So x times x is x squared. X times -3 is -3x. -1 times x is -1x. -1 times -3 is +3. If I go through and collect like terms, I end up with x squared minus 4x plus 3. And this is our standard form. So looking at this, right, we now know how to write our equations in the three different forms. Now the idea is what if we were given the standard form and we wanted to work backwards to our factored form? Could we do that? Well, based on what we learned in this unit with all the factoring, we should be able to. We should be able to convert from standard form back to factored form, which is why we were factoring in the first place. So let's go through and let's complete the following table for this quadratic equation. Y equals x squared minus 4x plus 3. So this is an equation in standard form. And again, standard form, y equals ax squared plus bx plus c. So if I want to find some of these key features, right? If I want to describe my graph, right? There's a couple things we have to do. And we have the steps here. So for our y-intercept, we're going to look at the c value. So our c value in this case is at the end here. So that means the y-intercept of this equation is 3. If I want to find the zeros, I have to factor. So I have to factor this equation. So if I have x squared minus 4x plus 3, or y equals x squared minus 4x plus 3, I need to factor. So if I want to factor, this is a simple trinomial, so I'm going to do product and sum, two numbers that multiply to 3 but add to negative 4. This is the same equation that we just looked at, so it's easy to factor because I know what my answers are going to be. It's going to be negative 3 and negative 1. So that means in my brackets, or in my factored form, will be x minus 3 times x minus 1. Now the next thing I need to do, if I'm trying to find my zeros or my x-intercepts, if you remember from last unit, our x-intercepts are going to be the opposite of what we see in the brackets. Or another thing that we could do is set each factor equal to 0. So x minus 3 equals 0, x minus 1 equals 0, and now I can go through and solve for x. I'll get x equals positive 3 and x equals positive 1. So these two values are my zeros or my x-intercepts or my roots. Right, so looking at these, right, this is a way that we can find our zeros. Now you may not need to set each factor equal to 0 in this case because it's relatively straightforward. It's the opposite of the ones that we've seen. However, we want to be careful because if we remember some of the factors that we've dealt with, right, some of the complex trinomials, some of the difference of squares, some of the perfect square trinomials, they may not end up being nice factors like this. Right? So this is where it's helpful to set each bracket equal to 0 or each factor equal to 0 and then solve for x. So now that we have it in factored form, we can go through and find all these other pieces of information similar to what we did in our last unit. Right? So our axis of symmetry, that middle value, I can find by adding my two x-intercepts up. So my axis of symmetry would be x value, so x equals 3 plus 1 divided by 2, or 4 divided by 2, which is 2. So this tells me that middle line, that line that's cutting our parabola down in half, or cutting our parabola in half, and I can use that value to find my vertex. Because I know for my vertex, it will have the x value of the axis of symmetry, so it will be 2, and then an unknown y value. To find that y, I can plug that 2 into my equation. Whichever one we want, it doesn't really matter. We can use the factored form or we can use the standard form. I'm going to use the standard form, so y equals x squared minus 4x plus 3. I get y is equal to 2 squared minus 4 times 2 plus 3. Y equals 4 minus 8, which is negative 4, plus 3, which is negative 1. And then this value goes back into our vertex. So our vertex is now 2, negative 1, which again matches what we saw from our graph. Direction of opening. So again, in this one, we just want to know if it opens up or down. If A is positive, it opens up. If A is negative, it opens down. So our A value in this case, if we go back up, A value is 1. So that means it is positive. Positive, so that means it opens up. Max or min value. Right, so it is going to be the y value of our vertex, so the value is going to be negative 1. And keep in mind, right, if it's, we'll highlight opens up, positive, opens down if it's negative. If it opens down, it's a maximum value. If it opens up, it's a minimum value. So because ours opens up, it is a minimum value of negative 1. And again, the minimum value is the y value of the vertex. So one of the reasons for factoring is if we're given an equation in standard form, we can go through and find all of this information. We can convert it into a form that is more useful to us because it gives us more pieces of information, or it allows us to find other pieces of information. So again, one of the reasons for factoring is to be able to change our quadratic equation to something more useful. So let's look at another example, negative 2x squared plus 8. So if I write out my standard form again, just to kind of have a reference, y is equal to negative 2x, sorry, not that one, ax squared plus bx plus c. So I'm going to label my values, my a, b, and c, just to help me out a little bit. So my a value is negative 2, my b value I don't have anything with an x, and my c value I can see here is 8. So we want to be a little bit careful, not just assume that because it's the second number, it's automatically our b value. In this case, it is our c value that's the second value. So our y-intercept from before, we just said it's our c value or 8. So our y-intercept is 8. For our zeros, we need to factor. So if I have y equals negative 2x squared plus 8, the first thing I want to do, it doesn't look like a trinomial, so let me factor, right? Let me common factor what I have here. It's not a difference of squares as well. But generally speaking, when we want to factor, we want to remove the value in front of the x squared. We're going to try to remove it when we common factor. So I'm going to take out a negative 2 as a common factor. If I take out a negative 2, I'm left with x squared minus 4. So the first thing we want to do is common factor. So negative 2 times x squared minus 4. And now this next one, in the brackets, looks like a difference of squares. That's one of the special cases that we dealt with in our previous lesson. So I can factor this because the square root of x squared equals x, the square root of 4 equals 2. There's two terms, they're separated by a subtraction. So I can rewrite this as y equals negative 2 times x plus 2 times x minus 2. So now I factored. So now what I can do is set the brackets. We called it factors, I believe. We go back, set factors. Set factors equal to 0. So x plus 2 equals 0, x minus 2 equals 0. And now I can solve. X equals negative 2, x equals positive 2. So those are our two x-intercepts. For our axis of symmetry, we'd said, okay, let's take our x-intercepts, negative 2 plus 2, we add them together and divide by 2. 0 divided by 2, or 0. So that means the axis of symmetry is 0. It's going right through the origin or right along the y-axis. My vertex now is going to be 0 and then a value. In order to get that value, I have to plug it 0 in for x back into my equation. So negative 2 times 0 squared plus 8. I can go right back to the original equation. Get y is equal to negative 2 times 0 squared is 0 plus 8 is 8. So our y-intercept in this case, our vertex is our y-intercept. Direction of opening, so our a value, if I go back up and look at my standard form or my factored form, my a value is negative 2. It's negative, so it opens down. My max or minimum value, because it opens down, we have a maximum value. The maximum is the y value of our vertex, so I have a maximum of 8. So again, we can factor our equations in standard form to find more information about our quadratic. Right? And now with all this information, I can actually go through and graph it. I know I have a y-intercept at 8. This is also my vertex. vertex slash the y-intercept. I know my two roots for my zeros at +2 and -2. So this is an x-intercept of 2, 0. This is an x-intercept of -2, 0. If I wanted to, I could just roughly sketch it. I do also know my step pattern, so I could use that because of that a value. That means I go over 1 down 2, over 1 down 6, and then I would go over 1 and down 10. So I can plot in those other points there. I can mirror that on the other side, and I can roughly connect those points and sketch my parabola. So originally, in standard form, I may not have been able to graph that. But by turning it into factored form, I now am able to find all this extra information that allows me to graph it. Another thing we might look at, we might be looking at just some kind of more application questions, right? So in this case, the trinomial 8x cubed minus 6x squared minus 5x represents the volume of a present, or the rectangular prism. We want to determine the dimensions of the present. So a hint, we want to think the volume, right? So volume of a rectangular prism, if we don't quite remember, volume equals length times width times height. So in this case, I should have three things that are multiplying each other. I have a trinomial that represents the volume. So volume equals 8x cubed minus 6x minus 5x, or 6x squared, sorry. If I want to turn it into a length and a width and a height, because when we're talking about the dimensions, we're talking about the length, the width, and the height, I'm taking this volume and breaking it up into three factors. I'm turning it into the product of three factors, right? Or three things multiplying each other, length, width, and a height. So in our case, we can try to factor this trinomial and see if we can get three factors. Well, looking at it, this looks a little bit different from our regular trinomials because of the cubes, the x cubed, the x squared, and the x. However, the first thing we should always look for is common factor. Is there a common factor? Well, there's nothing common between 8, 6, and 5 in terms of values or coefficients, but I should see that they all share an x. So I can actually take a common factor of x out. That would leave me with 8x squared minus 6x minus 5. Now, actually, let me just put this in a different color. Now, in the brackets is a complex trinomial. This now looks like something we can factor. So there's a complex trinomial here in the brackets. Now I'm going to leave the x on the outside. I'm not going to change that. That still gets carried through. But I'm going to look to factor the inside. And if I do the product and sum for a complex trinomial, I'm looking for two numbers that multiply to -40, or 8 times -5, and they add to -6. So two numbers that multiply to 40 and add to -6, or -40 and add to -6, we should have -10 and +4. So those two values multiply to -10, or multiply to -40, but add to -6. When it is a complex trinomial, we break up the middle term into those two values. So I have 8x squared. We'll try to keep it color-coded here. 8x squared minus 10x plus 4x minus 5. Oops. I'm going to look to factor by grouping. I'm going to factor the first two terms and the last two terms. In the first two terms, I can take a factor of 2x out. And that will leave me with, I'll have to change our brackets just so we don't have all the same and you don't get confused. So we'll take a factor of 2x out. That leaves me 4x minus 5. In the second pair, there's nothing I can really take out, so I'm going to just take out a factor of 1. That's all that's common between them. And I kind of need a placeholder. So 1 times 4x minus 5. I can factor by grouping, or factor the common factor of the bracket out. So I'm left with x times 4x minus 5, and the remainders 2x plus 1. So now I have my volume represented as the product of three factors. I could call it a length, a width, and a height. Because it's a rectangular prism, it doesn't really matter which one is which, right? Because if I have my present as I see up here in the diagram, I could also have it differently. Maybe I stand it up vertically, right? And then the dimensions that I originally called the width and the length are now opposite, right? Maybe it's now a length and a height, right? So when we're dealing with volume or length and width and height, the order doesn't really matter when we're talking about the dimensions, as long as we recognize that I have three different factors here to represent the three different dimensions. So again, another kind of application of why we might want to factor. If we have an expression for the volume or expression for something and we want to break it down into dimensions or into the products, we're going to have to factor, because we're going to have to revert it back from an expression into the factors itself. So again, some examples of how to, or some applications, of factoring. The primary one that we're going to be really using is how to solve or how to find different values of our quadratic by converting our standard form back to factored form. But there are some applications as well, like we saw here. So again, make sure you do understand how to factor different types of quadratic expressions or just expressions in general, because that is going to be important when we use it in these applications.